Okay, so again, just to remind you all that this is in that handout and the link of the 2.2, I just want to make sure that we cover it together, that given y equals f of x, right, the common notation for the derivative is f prime of x or y prime of x, but it's not the only one. So in this particular case, we mentioned last week that dy dx is another notation for the derivative, and it's read the derivative of y with respect to x. The derivative of y, so your function in some variable of x. And then again, so that's separate. Another notation that you'll see here that we mention is df dx, and again that is read the derivative of f with respect to x. Another one that you'll see that we use is the derivative d with respect to x of f of x. So d, a lot of times players, get this notation, dy dx is different than d over dx of f of x. And so d over dx is that differential operator. And then another one that you may see, different textbooks of course have different notation, but capital D of f of x, this is another derivative operator. And then in this case here, if we're dealing with higher order derivatives, then you'll see here d with respect to x of f of x. Common ones that you want to make sure that you're familiarizing yourselves are, let's just count, 1, 2, and 3 would be the common ones that we are going to be using. And so we also talked about here is evaluating the derivative at some particular value. And this is just illustrating that a function f is differentiable at a if f prime of a exists. And we stated that if f is a piecewise function, then the left-hand derivative must equal the right-hand derivative. And again, f prime of x exists if and only if the left-hand derivative equals the right-hand derivative. Then it's differentiable on an open interval if it is differentiable at every number in that interval. So that means that that limit notation for any value of a, that limit notation will exist. So when you take a look here, how do we show if a function is not differentiable at a particular value? Well, it's going to require some work, and that's going to require us to use this particular definition. And in order to use that definition, you're going to have to take f of x as we did last week, but I didn't use this definition, so I just want to make sure that we're all on the same page here, is that this would equal a minus x if x is less than 0, and x if x is greater than or equal to 0. And so if I'm taking a look at f prime from the left at 0, then this is going to be the limit as h approaches 0 from the left, and then here we're putting 0, here we're putting 0. So in this particular case, this is going to be a minus h, which is going to be minus 0, which is going to be all over h. And so therefore, this is going to be the limit as h approaches 0 from the left. Since this is 0, these h's reduce and you get a -1. The limit of a constant is a -1. Then when you take a look at f prime from the right at 0, again, we're replacing 0 here and 0 here. So when you evaluate your function, you're just replacing h. So that's why you get, I forgot to write the limit. As h approaches 0 from the right, this is now going to be h minus 0, which is going to be all over h, which you're going to get the limit here as h approaches 0 from the right of 1, and you get 1. And so since the derivative from the left, from the left of 0 does not equal the derivative from the right of 0, then therefore f is not differentiable at 0. And this is a little bit more work than I was dealing with last week because we were pressed for time. So last week we were using the power rule to justify it. So please make sure that we follow the directions or we may get points reduced. So a big theorem, big theorem. If a function is differentiable at a, what it means is that f prime of x will equal the limit as x approaches, nope, just kidding, as h approaches 0 of f of x plus h minus f of x all over h. So this is saying that if this exists at any value of a, then the function is continuous. Well, what was the definition of continuity? Then the limit as x approaches a of f of x will equal f of a. So again, right, this is that if P then implies Q. However, you can't reverse this. So what this is saying in the counteract of this is that what this is going to illustrate here, let me erase this, that it is true if a function is not continuous, then we could say that it's not differentiable at a. However, it is not true that if a function is continuous, then that does imply that it is differentiable. And these are some concepts that are going to take some time for us to kind of get under our belts. And so we're going to take a look here, is that the absolute value function is continuous at 3, but it's not differentiable at 3. And that's the legwork. Because in order to show a continuity, then we're going to have to take this function, f of x, which equals the absolute value of x minus 3. And be careful from the last time, because remember I had that error because of the reflection. So you just have to be mindful of that. That this is going to be a minus x minus 3 if x is going to be less than 3. And this one is going to be x minus 3 if x is greater than or equal to 3. And 1 to verify continuity, then f of 3 3 minus 3 is going to be 0, so check that that exists. 2, we have to verify the limit as x approach 3 from the left. What are we using here? A minus x plus 3. Does this equal the limit as x approaches 3 from the right of, what is this, x minus 3? And so when you replace this here, you notice that you get 0. And when you replace this here, you notice that you get 0. So since the left-hand limit and the right-hand limit equal, then we're able to say the limit as x approaches 3 of the given function f of x does equal 0. And you make your conclusion that since the limit as x approaches what? 3 of f of x equals 0, which equals f evaluated at a. Since those are equal, therefore f is continuous at a equals 3. Now, to verify if this function is, so this is showing you here that this function is continuous. So if it's continuous, can we imply that it's differentiable? No, we can't, and I'll show you. Because now, to find f prime from the left of 3, which equals the limit as h approaches 0 from the left, f of x plus h. So when you evaluate f of x plus h, or in this case 3 plus h, then this numerator is going to become a minus 3 plus h minus 3 minus f of 3, which is 0, which is going to be all over h. When you distribute here, this is a negative 3, this becomes a positive 3, the 3's cancel, the h's reduce, so therefore you get a limit as h approaches 0 from the left of 1, which equals 1. And then when you evaluate f prime from the right of 3, then you get the limit as h approaches 0 from the right. And now that's going to be 3 plus h minus 3 minus f of 3, which is 0, all over h. The 3's cancels, the h's reduce, so you get the limit as h approaches 0 from the right of 1, which equals 1. And so, therefore, right, f prime from the left of 3 does not equal f prime from the right. I'm having a hard time squeezing this in. I don't know why it's acting up of 3. Says they don't equal, then f is not differentiable at 3. So a function can be continuous at a value a, but doesn't have to be differentiable at a. But if a function is differentiable at a, then it must be continuous at a.